Okay, Sisson, 7.4. Everybody's got me a look through 1 through 20 and pick 3 problems. 1 through 20. Pick 3 that you'd like to see work. Look at them and see what looks weird. Look at them and see what you'd like to see me work.
Number 7.
Number 7. Okay. What else? 1 through 20. Pick 3.
19.
19. All right. And what else? This is your chance to look at there and go, well, I might not be able to work that one. I kind of want to work number 12. But I'll work anything you want. Number 12, okay? All right. Number 7, here we go. And this will be a review of everything we've been doing. So here is number 7. -1 over the square root of 48 equals 1/8. All right. Sine x equals 1/8. Now, folks, I'm not sure about this. I think I'd take the reciprocal of both sides. A fraction equals a fraction. Just take the reciprocal of both sides. Or you might realize that these two denominators are going to have to be equal with the negative sign because the two numerators are equal, right? Okay? But if you take the reciprocal, you get negative square root of 48 sine x equals 8. I keep looking at square root of 48, and I keep thinking that would reduce. That doesn't look right to me. That's what? 16 times 3? And why did I pick 16? That's right. That's really -4 square roots of 3 sine x equals 8. So sine x really just equals -2 over the square root of 3. And at that moment, I realized we got a problem. Because that's going to be a number bigger than 1 or smaller than -1. Sine can never equal a number that's bigger than 1 or smaller than what? -1. The sine of x will always be between -1 and 1. Well, that's only 1 point something there, right? Square root of 3. So that's going to be like -1 point whatever is decimal. So this is an empty set. All right? And of course, I slide over here slowly and look on my check. Yep, empty set. Make sure I didn't make some kind of little mistake. Because if the sine x would have been up here, it wouldn't have been empty set. All right? It would have worked. Okay, it's empty set. Somebody says, that's awful close to what's on our circle. Yeah. I'm thinking when he made out the problems for the book, he may have messed up there and then realized he's going to have to put empty set because he may have wanted it to work. Okay? Number 19. Number 19. Cotangent 2x. Good. This is one of the ones with the... I'm going to put the 2x in parentheses. It just helps me see it. Cotangent 2x over the square root of 3. Is everybody okay if I go ahead and just multiply the other side by square root of 3 and put negative square root of 3 equals negative square root of 3? And my problem is cotangent is not easy for me to look for on my circle, is it? I just multiplied, yeah. Is everybody okay that I'm just going to do what? I'm going to take the reciprocal of this and call it what? Tangent. Yes, ma'am, you're a step ahead of me. And I'm going to make that -1 over square root of 3. And then now, you see the 2x in there, right? This is one of the ones where you've got to do everything in terms of theta. And you've got to go around the circle how many times? How many times? Yep, go ahead and be bold. 2. You've got to go around the circle 2 times, right? Miss Flowers, be bold. Now, you need to write theta equals 2x right here so that you'll know what you're doing and why you're doing it. Okay. Somebody tell me what happens when you go around the circle once. Okay, where does the tangent equal -1 over the square root of 3 first time around the circle?
5 over 6 pi.
5 over 6 pi? That's a negative, right? Yeah, 5 over 6 pi. And where else?
7 over 4 pi.
Oh, no.
11/6 pi.
11/6 pi. Yeah, you're looking at enough. Okay. Sine. Yeah, that's right. All right. Now, but I got to go around the circle again. So what do I add to this? 2 pi, which is 12/6 pi. If you have to, write down what it is. So 12 is going to be 17/6 and 23/6. Man, yeah, see? Makes me look good on film. Kids get the right answer. Now, those are your thetas. How do I know I have to go around the circle twice? Back row, because what number? 2. Yeah. Then all I got to do is determine x. And the easy way to determine x is realize that x is going to equal 1/2 of theta. So x equals half of that, 5/12 pi. Half of that, 11/12 pi. Half of that, 17/12 pi. Half of that, 23/12 pi. And do you notice how that's getting real close to 2 pi? See how that got real close to 2 pi by the time you got the last answer? Take half of all those. And I just want the solutions between 0 and 2 pi. Now, I'm going to teach you and show you how, yes sir?
Where did you get the 1/2 theta?
Okay. Theta equals 2x. Remember I told you had to write that down? That's so I can figure out what x equals. Because if theta equals 2x, what does x equal? Half of theta.
Oh.
Yeah. See, if you don't write this down, then you don't know what you need here.
So say you had like for tan 2x instead of that you had tan like x over 2. Like what would
Then you only go halfway around the circle. Yeah. And then when you get down here, you'd have a 2 times it right there. So if you have this equation, then you ought to be able to figure this one out, right? Now, say that was a 5 right here, right? You have to go around the circle 5 times. You're going to get a whole bunch of answers. But then what do you have to do to all of them? You take what? 1/5. But you don't have to already be thinking about this. You just got to make sure you write this down so that you can use it here. All right? I'll write that down so that I can figure that out. And when you make the list, you need to label which one is theta, which one is x. Because if you don't, it gets real confusing. You've got to label your work now. There's too many possibilities not to. All right, now, someone says, Mr. Evans, I looked in the back of the Sisson book, and that's not what the answer is. He said the answer is this. All right. What did you add? What would you add 5/12 to get 11/12? You would add what? 6/12, right? Six twelfths is what? Pi over 2. What did you add to 11 to get to 17? You added what? 6/12. So what he says is the first number is 5/12 pi, and then n is always a whole number, 1, 2, 3, 4, 5, okay? And you just add pi over 2 to get to the next one, pi over 2 to get to the next one, pi over 2 to get to the next one. And every time see if you put a 5 there, or put a 4 there, you would add 2 pi to that, which would be 17. Be that one right there, see? See what I'm getting at? And that's how he writes the answer so that they go out to infinity. I don't really want you doing that, but when you look at his answers, it's really easy to get the answers I want, because you just put a 1 there, then put a what there? 2. And the first time you put a 0 there to get what? 5/12. Everybody okay with that? Everybody all right with that? Yeah. So you just start off with n equals 0, n equals 1, n equals 2, and it'll make that list for you. I would say this is the shorthand for writing all that out. Plus, this gives you a list all the way out to positive infinity and negative infinity. If you start putting -1, -2, -3 here, you start getting the negative values that would work. All right? but I'm not gonna require you to write like that, I just 0 to pi.
Mr. Evans, if we put that shorthand on the
I'm
text.
gonna mark it right as long as it's right, yeah.
Okay.
Yeah, oh yeah, 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 oh yeah. Not gonna complain a bit if you do that. All right, last problem, number 12 from this section, number 12. Here we go, number 12. Someone look at number 12 and think, why did Mr. Evans give us this one? Why did Mr. Evans give us number 12? What's he hoping to happen? Mr. Evans is hoping one of us realizes something. How you doing? Ooh, thank you. What am I hoping you see? Oh, I like that. Somebody's already looking on the back of their circle. Because they know anytime we're hoping you see something, it's usually written on the back of your circle. All right. What am I hoping you see from the back of your circle? Yes, sir.
It's on the right side, one.
That's right. That's the mother. That's the mother identity right there. You just saved yourself a ton of work. You recognize the mother identity. That's the mother identity. Guy by the name of Toynbee. Toynbee. He wrote a book called Mankind and Mother Earth. Okay? Toynbee. Toynbee is one of the great historians from England. He survived World War I because he missed the boat. He was sick, and maybe in World War II, but I think it was World War I. Anyway, he was very ill, and when his group shipped out, he couldn't ship out because he was in the hospital, and the ship that he would have been on was sunk by a U-boat, and everyone on board died. And he went on to write a lot of history. He writes history in an unusual way. Y'all used to doing history chronological, right? To do chronological history. He doesn't do that. He takes a concept of, say, marriage, and he looks at it all over the world, and, you know, like, how did it develop in China, how did it develop in Southeast Asia, how did it develop in India, how did it develop in Germany, how did it develop in Spain, and then why it developed different ways in different parts of the world. So his history is more like topic history. He picks one topic and covers it all the way through, and then picks another topic and watches it go all the way through. It makes it a little hard to read because you have to skip around from different groups. But Toynbee wrote the book Mankind and Mother Earth. He's considered the great English historian of the 1900s. Does anybody know who the great American historian is from the 1900s? Will and Ariel Durant. And the reason I put Ariel's name on there is because she wrote the books with him, even though she never formally went to college. But Will and Ariel Durant. She was educated at Columbia, but she was not registered for any courses. She just went to Columbia University in New York and went to the classes that she wanted to go to and listened. Yeah, didn't have to study for tests and all that. She just went and listened. And she wrote a lot. She did a lot of writing, but Will and Ariel Durant, they're the Americans. And their story is a little bit crazy. He thought he was going to be a priest, and he decided he wasn't going to be a priest. His mom had a bad day when that happened. Sin squared x equals 1. Get back on track. You're going to take the square root of that 1. When you take the square root of that 1, it's not just a 1, it's a what? Positive or a negative 1, right? Now, you look on your circle and you tell me, where does a sine x equal a positive or a negative 1? Nope, not pi over 4. Either your circle's wrong or something.
Pi over 2.
Pi over 2. And where else?
3 over 2.
3 over 2 pi. And just so you know, that's how the answer would look if you looked at Sisson, yeah. All right, because you can see that you're adding a pi each time. Okay, now look down the page, because y'all are first hour and I've got lots of energy. Later in the day, this won't happen. Look down the page, and I will work on any of those. Well, yeah, look down the page and just pick one you'd like to see work. One problem from anywhere else that there's an assigned problem. Pick an assigned problem and I'll work it. You get to look down the page and pick them out of the toughies.
Number 73.
Yeah.
73. Oh man, what? 73. Hey, to tell you, that's one of the easiest problems on the page. It just looks bad. That's my kind of problem. Hadn't even looked at it. Mr. Evans hadn't even looked at it. Oh gosh, maybe it's not the easiest problem on the page. 73. It's like, well, give him something to do for the rest of the day. 2 sine x cotangent x plus square root of 3 cotangent x minus 2 square roots of 2 square roots of 3 sine x minus 3 equals 0. All right. Cotangent x is really cosine over what? Sine. What I want to do is multiply everything by sine so that I don't have that cotangent there. But I'm going to tell you that's not the best way to work it. All right? But that's probably what a lot of people would do. They would say, well, if you look at that, you could write that as what? Cosine x over what? Sine x. Oh, then what do the sine x's do to each other? Cancel out. Plus square root of 3 cosine x over sine x. But then, does anything divide out for me? No. And all of a sudden, I've got a fraction that I'm going to introduce a fraction into the problem. Introducing fraction into problem. Which, you know, I just don't like that. Don't like in doing that. But here's your moment. So we're going to quit doing that. Notice I'm showing you why I don't like it. I think it'll work if you keep working, but I don't like it. Okay, I want you to look at this in the middle. Notice how you have sine x times cotangent x. Here's what I'm going to do. On the end, I know my numbers have to be a 3 and a 1. And I know that I have to have a sine x here and a cotangent x there. Because what is sine x times cotangent x? Cool. Now, the problem is that's not where the 1 needs to go. Oh, it's square root of 3 though. Well, Mr. Evans may have just sent you down. I got to see if I wrote the problem down right. Oh, yeah. This needs to be a square root of 3 here. And this needs to be a square root of 3 here. Because square root of 3 times square root of 3 is what? 3. And why am I thinking square root of 3? Because, oh, look right there. Square root of 3 times cotangent x is what? That one. I'm going to put a 2 here. I'm going to put a minus here and a plus here. Let's see what happens. 2 sine x times that would be what? Negative 2 square root of 3 sine x. All right? That's a hard problem. That's a problem that requires, but it is, you can factor it. Now, someone in another class is going to say, Mr. Evans, that's not the way to teach them to factor it. Okay, let me show you another way to factor it. Because I just saw that term, if you multiplied those together, it would give you this. And then this one and this one would give you one of the terms, and this one would give you one term. That's probably not how I'm supposed to teach the factor. Let me show you the other way to do it. All right? I'll show you the other way to factor it. Y'all remember this thing called factor by grouping? If you factor cotangent x out of both of these, is everybody okay? I'm going to factor cotangent x out of both of those. I would get cotangent x, and then I would get 2 sine x plus square root of 3. And then I'm going to factor out a square root of 3 out of both of these. I'm going to factor out a negative square root of 3 out of both of those. And that's going to leave 2 sine x, and I'm minus be a positive square root of 3. And do you notice how after you factor that out, these two are the same? Remember when you were doing factor by grouping, if these two were the same, you could bring that to the front, factor it out. And then get cotangent x minus square root of 3. That's called factor by grouping. And that's one of those things we teach you and you have 4 terms. If you ever have 4 terms, you can do factor by grouping. I didn't do factor by grouping up here. I just knew those two would give you that. Square root of 3, square root of 3. But that's how you probably would be taught to do it. Set each one of those equal to 0. Look it up on the unit circle, right? Do I need to do that part? I do. Sine x equals negative square root of 3 over 2. And cotangent x equals square root of 3. But I am not going to look for that. I'm going to do tangent x equals 1 over square root of 3. And then I'll let you look for the answers on your unit circle. Yeah, that was the last one on Sisson's book. Oh, look at 74 down there. Man, those are bad. 29? 29 is X'd out because you'd have to have a calculator. Yeah, I didn't give you anything where you'd use a calculator. That way, because if you can do this, anybody can punch the buttons into other ones, I guess. All right. Now, that should give you a pretty good start on working some Sisson problems. If you're not into Sisson pretty soon, you're not going to be ready for next Monday, right? Everybody follow that? Yeah, you're not going to be ready for next Monday. This should get you pretty close. All right. I've worked